Okay, how's it going, guys? Back in for another recitation. I think this is the second to last recitation, so should be pretty cool. Thanksgiving is coming up, obviously, and an exam is coming up, so it's a pretty useful one for that. So let's just get right into it. Don't want to make this too long of a video. First one, it's going to be a really basic head loss and pumping power problem. So what we got here is we have water being pumped at, that's 3 liters per second, right? 0.003 cubic meters per second, into the top of the truck through a 40 millimeter diameter hose. If the length of the hose from C to A is 10 meters and the pipe is smooth, determine the power output of the pump. All right, so what I like to do before I even do anything with these problems, before I even determine what to find, do any of that, I just like to get kind of the general parameters of the problem, right? Try and get the velocity of the problem, the mean velocity in the pipe, and the Reynolds number. So let's do that. I'll do this on this back page over here. So first off, we're given a volume flow rate, right? So we know Q equals VA. And so with this, right, we also have a diameter. So we can just directly solve for velocity just straight up. So V equals Q over A. So if you go plug in those numbers, you get V.03 over pi times 0.02 squared, because it's 40 millimeters. So the mean velocity in the pipe is going to be 2.387-ish. 2.387 meters per second. All right. And so with that, let's just directly get a Reynolds number now, so we can determine if it's turbulent or not. And so that, of course, is our rho VD over mu. And we're just using water, so we can just put in 1,000 and 1.003 times 10 to the negative 3. So we've got 1,000 times 2.387. Okay. And these, right, the density and dynamic viscosity, those are just, whoa. Those are just really good numbers to put on your cheat sheet if you need to remember them, right? So we'll get a Reynolds number of about 95,207. And so, of course, this is turbulent, right? Because RE is greater than about 2,300. Cool. All right, so we found the general parameters of flow. So now let's try and find what we're actually looking for. All right, want to determine the power output of the pump. All right, now if you think back and go, well, we've done stuff with power before, right? And you just didn't know it in like the way you're looking at it now. But if you remember way back, you did some stuff where W dot of a pump is equal to rho G Q times HP, where before, right, and you did this in terms of like mechanical energy problems, where we just give you this HP and just say, hey, take our word for it, this is what the pump head is, and then you do this problem. So with that, right, we need to find some HP. We need to find HP. And so how do we do that? Well, let's do our energy equation and see what all we need to find, right? So if you look back here, we're going to be going from point C, which is right on the free surface of this lake, to point A up here, which is the top of the hose. And for the sake of this problem, all right, I pulled this from a textbook, and it doesn't say it in here, but we're going to assume that both of these points are open to atmosphere, all right? Just imagine you're like resting the hose on the side of this tank, whatever. So let's do it. Let's use our energy equation. Right, where this alpha term, I guess you guys hadn't really seen this alpha term. This alpha is just the laminar turbulent kinetic energy correction factor, I think is what they call it. For all you need to know, if the flow is laminar, alpha equals 2. If it's turbulent, alpha equals 1. So that's really all you need to know about it. But let's clean up this equation. So I said they're both open atmosphere, so we can get rid of the pressure terms. I said point C is on like the free surface of a big lake, so we can call that velocity 0. We can also say ZC is 0, right? That's our datum point. We can call it 0. Let's see what else. There's no turbine. That's pretty much it. So we're going to have HP is equal to, and alpha is equal to 1, right? And VA is just the velocity in the pipe. So we're going to have V squared over 2G plus ZA plus HL, our head losses. So let's go find our head losses. Remember, HL is equal to F L over D V squared over 2G, which is our major losses, plus our minor losses. Which in this problem, they don't give us any minor loss coefficients or even mention it at all, so we can go ahead and get rid of that too. So all I need to worry about now, really, all we need to do is find this F, our friction factor, and we're good to go. And in problem 2, I will do an iteration one. So for now, let's just use our Moody chart. Use Moody chart for F. And it's given in the problem that the pipe is smooth, right? It says if the pipe is smooth, blah, blah, blah. So epsilon is equal to 0 in our case. And so now we're going to use the Moody chart. Show you how to use the Moody chart if you don't know. So in our case, right, you always start over on this right-hand side if you've got like epsilon over D and you know the Reynolds number and all that. So let's find our epsilon over D. So we said ours is 0, so you're just going to start way down in this corner, okay? And now you're just going to follow one of these lines, right? In our case, we just follow this very bottom smooth line, so it'll be easier for me to do like this. And you follow it along until you hit your Reynolds number along the x-axis. And ours was 95,000. It's basically 100,000. Should be right about there-ish. Kind of like smack right in between those two lines, right? Kind of something like that, if you can see that. Sure, zoom in, whatever. All right, so you do that. Then you just go straight over. You just go straight over after that. And kind of line it up on this other axis over here. And kind of go like that. Cool. It's just a good estimate, right? I'm not a huge fan of the Moody chart, actually. But whatever. So you can say like what? 16, 17, 18. We'll call that like 0.018, I guess. Sure. I'll say ish. All right, good enough. Hey, whatever. For the record, when I did this problem, I did the full iteration and I got like basically the same answer. So whatever. There's margins of error for this stuff. Don't worry about it too much. So let's find our actual value for this. So we got HL is equal to, we said what's the length of it? 10. So you should get HL is equal to, where's my number? 1.319. Again, ish, right? It depends on what your friction factor ended up being. So let's plug that in. Okay, HP is equal to 2.387 squared over 2 times 9.81 plus ZA, and ZA is just 5, right? 3 plus 2 is 5. 5 plus 1.319. So you get HP is equal to 6.609 meters. Now with that, right, just plug directly into W dot P is equal to rho G Q HP. So we get W dot P is equal to 1,000, 9.81. So we get W dot P is equal to about like 194.5 watts. Give or take, right? We're pretty lenient with the rounding. Just be careful when you round, right? I've been giving people like a 5-10% margin of error, which is generous. Whenever, if someone, like I was grading the homework, and if you get a weird number, I just go back and make sure your work is right. And if you rounded weird, I'll just be like, hey, don't round so weird. I don't know. Whatever. So that's problem one. That's the easy one, right? If we give you a flow rate and you can find a velocity, you kind of go in that direction, right? For this next one, it'll be opposite. I'll give you like a delta P, and you'll have to work your way up and go find a flow rate from that. It's a lot trickier, a lot more tedious. So let's do it. So if you read here, okay, this one, we've got a petroleum company must send oil with specific gravity 0.88 and kinematic viscosity nu is equal to that through a 10 centimeter diameter asphalted cast iron pipe with epsilon equal to 0.12 millimeters. And we'll always give you these values, right? Or we'll give you like a table with these values. You won't have to solve them. And we're pumping at an unknown volume flow rate, right? The pipe is 100 meters long and slopes upwards at 8 degrees in the direction of flow. There are also two 9-degree elbows present. Make sure the pipe navigates around a large boulder. The minor loss coefficients rated these elbows are KL equals 0.9. Again, we'll give you these, or we'll give you like a table to read, right? Not that big of a deal. Calculate the head loss and meters and volume flow rate in this situation. Through testing, they know that the pressure change between the two ends of the pipe is 680 kPa, and the flow is fully turbulent. Assume there are no pumps or turbines in the section of pipe being analyzed, and no other sources of loss are present in the system. This is also kind of a more realistic problem too, right? It's a lot easier to determine a delta P instead of volume flow rate, right? You just stick a pressure transducer in two ends of your pipe. It's pretty easy. But I'll try to quickly redraw this situation. So imagine, right, we've got this pipe here, and this kind of has a little tiny kink in it to make sure it goes over some boulder, all right? We'll call that 8 degrees right there. And this diagonal length, we'll call this 100 meters. Okay, and we're assuming that this little teeny tiny kink doesn't contribute anything to the actual length of the pipe. So we're gonna have this, this will be point A, this will be point B. And also assume that this pipe goes on forever and that there's no pumps or turbines inside this length of pipe, right? We're just looking at this little tiny length. But our delta Z, so it's just going to be 100 sine 8 degrees. And so delta Z is equal to 13.91 meters. All right. So like I said, we're going to have to do this problem in reverse from what we did last time. And so we're given a delta P, okay? So what's our only equation we really know that relates some delta P's and head losses and stuff? Well, it's just our energy equation, all right? So let's start with that. So let's just rewrite it. And again, we know the flow is fully turbulent, so its alphas are going to be 1. So let's go. Right, and again, we said no turbine, no pump. ZA, we can call that 0. And think about this pipe, right? Due to conservation of mass, we're going to have the same velocity inside the pipe at both ends, right? If we have a constant flow rate, constant density, all that stuff, we're going to have the same velocity. So we can just, right, if I were to subtract VB over, right, they'd get each other cancel. So we can cancel those velocities too. So now all we're left with is, we've got PA over rho G is equal to PB over rho G plus ZB plus HL, right, where we're trying to find this head loss. And so what do we want to do? Well, if I subtract this PB over rho G over, PA minus PB is literally our delta P, right? So let's just isolate HL in terms of delta P. So we end up getting HL is equal to delta P over rho G minus ZB, where ZB is just our delta Z, right? So we got HL is equal to 680 times 10 to the 3 Now, what's our density, right? Well, I gave you the specific gravity. So 0.88 times 1,000, right? Specific gravity is the ratio of like your fluid in question. And then in our case, the ratio to the density of water. So 0.88 times 1,000, that's 880. And then gravity, 9.81 minus 13.91. All right. So for this first bit, you end up getting HL. The head loss is equal to, where's my number? 64.86 meters. Cool. And so, right, if you were doing like, if your boss wanted you to calculate like the volume flow rate, this would be like a good intermediate step. You know, hey, these are the friction losses in the pipe, so this will affect my flow in yada, yada, yada ways, right? And you go tell your boss that, and he'd go and do something. But for us, we want to get a volume flow rate. So we need to relate this HL equation, this HL number, to our velocity, right? Because from a velocity, we know the pipe diameter, so boom, we can get a flow rate. So what does HL actually equal? Well, HL, of course, equals F L over D V squared over 2G plus sum of KL V squared over 2G. Or again, right, we don't know F, we don't know V, but we know everything else. So let's write down what we know. And then, so the sum of KLs, right, we have two elbows and they're both 0.9. So 0.9 plus 0.9 is 1.8. And V squared over 2 times 9.81. All right, now I skipped some algebra steps here, but it's really not that big of a deal. What you want to do, you just want to get all of these constants out of here and just get an equation of F's and V's. So what I did is I, turned all of these constants into just like numbers out front. And then I divided some stuff over and, divided 64.86 by these numbers here. And then I factored out a V squared. So I end up getting, for like an intermediate equation of 1.272 is equal to V squared F plus 0.0017991. And right, and I carry out a lot of decimals here because it's, important when you're going to be like iterating and whatnot. So one last thing, I divide this F plus blah, blah over and then square root the whole thing. So I have V as a function of F. So we end up getting V is equal to 1.1278 divided by the square root of this F thing, F plus 0.0017991. Cool. All right, now I'm going to put a box on that because this is one of the equations we're going to use to iterate. Okay, now it's time to iterate using Colebrook. All right. Iterate, okay? And how are we going to do this? These are our steps. These are our steps right here. Going to guess an F1, solve for V1, find a Reynolds number, and then find another F, find another F2, and repeat. Right, and you find another V2, another RE2, yada, yada, okay? Repeat until the numbers stop changing, all right? So good place to start, okay? We're going to be using Colebrook equation. So let's guess an F. So F1, we're going to say F1 equals 0.02. That's where I always start. You don't have to, but it's whatever, all right? Now, for V1, I'm going to plug this in. All right, so you end up getting for V1, it's like 7 point something, 7.638. All right, now let's find a Reynolds number. And I didn't give you the dynamic viscosity, so we can't use the density version of it. You have to use the kinematic viscosity version of it. That's easy, it's just VD over nu. It's the other version. And so we get RE1. is equal to 7 point blah, 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 what, 638 times 0.1 over 4 times 10 to the negative 5 is what our kinematic viscosity was. So RE1 is equal to, blah, 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 where's my number at? 19,096. All right, and now plug this into Colebrook, okay? Colebrook. This is 1 over, on the left-hand side, we have the one we're solving for. So this will be root F2. So to negative 2 log, and this is log base 10, right? Not natural log. 2.51 over RE1 root F1 plus epsilon over D over 3.7. Right? So just plug in all the numbers on this right-hand side. We've got the stuff on the right-hand side, so let's do it. Yeah, 2.51. And our epsilon is 0.12 millimeters, so 0.12 times 10 to the negative 3 over 0.1, 3.7. Right, so this just spits out a number, okay? Negative 2 log of some number. I square both sides, take the inverse of it, spits out F2. Okay, so F2 is equal to 0.02968. All right, and now repeat. I'm not going to do the full thing again, don't worry. Repeat. And so if you went and repeated again, right, we'd have V2, plug it back into that same equation, right? Plug it back into this equation. V2 should be 6.355. Again, plug into Reynolds number again, right? Reynolds number should be 15888. All right, do another Colebrook equation. Should get F3 should be equal to 0.0296 and change, like 93 or something like that. Well, hey, boom, look at that. We're pretty much done, right? Match. I always say you can stop when it matches to the 10,000th place, which it sure does. Hey, close enough. Close enough. Sweet. And so just for shits and gigs, I guess, plug it into the velocity equation one last time. So I'm getting V. V is equal to, our final velocity is equal to 6.364. Right, and between these two numbers, right, it changed to like 1/10 of a meter per second. That's good enough. Right? And now how do we find a volume flow rate? Well, just plug it back into our volume flow rate equation. Q equals VA. We've got Q is equal to 6.364 pi 0.05 squared. So I'm getting Q is equal to 0.05 cubic meters per second. And I know that answer is right because I'd originally written this problem. I wrote this problem myself. And I'd originally written it that I gave you the volume flow rate and I wanted you to find a delta P, but the professor was like, no, it's too easy. Make him do the other way around. So I erased everything and went the other way around and it spit out the same number that I'd started with originally. So, bam. But yeah, as you can see, this is a case of like double iteration. So it's a little more tedious, but when you get to the exam, if you have to iterate like 7, 8, 9 times, you did something wrong. We'll pick the numbers such that it only takes, like 2 or 3, like what I did here. As long as you pick your numbers relatively well, like your initial guess, right? Don't pick F1 as like 100, right? You know it's going to be small. So try and logically think your way through this stuff. But yeah, this exam is very pluggy-chuggy. Just trust your equations, trust your laminar and turbulent flow stuff, and I think everyone should be all right. Anyway, if anyone needs anything, just shoot me an email. Let me know. Drop a comment in the video. Thank you.